Okay, thank you. Hello, everyone. I have the honor to introduce our first invited speaker today, Professor David Xu from National University of Singapore. David is a Provost Chair Professor in the Department of Computer Science, National University of Singapore, the Director of Smart System Institute, and also the founding director of NUS AI Laboratory. He received his Bachelor in Computer Science and Mathematics from University of British Columbia and PhD in Computer Science from Stanford University. He is an IEEE Fellow. His research lies in intersection on robotics and AI. In recent years, he has been working on robot planning and learning under uncertainty for human-centered robots. His work won multiple international awards, including most recently the Test of Time Award at Robotics Science and Systems in 2021 and Ijikai JAI Paper Prize in 2022. He has chaired and co-chaired several major international robotic conferences, including WAFR 2010, RSS 2015, ICRA 2016, and the CORL 2021. He served on the editorial boards of International Journal of Robotics Research and Journal of AI, Artificial Intelligence Research. He is currently an editor of IEEE Transactions on Robotics. Let's welcome Professor Xu.
Thank you for the introduction, and thanks to the organizers for having me over here. I have one major advantage today. I'm local. I'm totally awake, right? For those of you who are coming down from US, sorry for you guys. And the US, this is almost like close to midnight for you. And this is one of the few times when I have the opportunity to speak when I'm actually fully awake. And hopefully that leads to better improved performance. I'm going to talk about planning, robot planning, and the robot planning in the open world. Oftentimes, when we talk about planning, we are in the AI planning community, where we are actually thinking about our planning methods, right? The search algorithms, constraint satisfaction algorithms, and these days the large models that were able to predict or construct a plan given a model of the world. That's what. But I'm not going to talk about that today. Many of you know a lot about this, as much as I do, probably more than I do. What I want to talk about today about robot planning in the open world is how do we come up with models? How can we make planning actually work for robots in the open world? And towards the end, if I still have some time, I want to touch a little bit on failures. All models are wrong. There is a gap between a model and the world. That leads to the failure of the plan, oftentimes in the real world. And towards the end, I will touch on that a little bit if I still have time. Right? So let's start by a concrete example of the open world, right? So if you're not from Singapore, you want to come to my office, right? So you come to our school computing building for the first time. You don't have a 3D world model of this building. You have never been there, therefore you have no data about that interior either. And all you want is I gave you my office number and you will come to my office. And one way or the other, most of you will succeed on this task. We are sure about that for us humans. We are so good at this. So this is an instance of the open world planning problem and robot task, right? This is what I want to do. Now, this is a problem that fascinated robotics ever since for as long as there is robotics, right? And ever since the beginning of robots, the famous shaky robots, right? A human engineer will manually construct a model of the world. In that particular case, back so many years ago, more than 50 years ago, that will be called a 2D occupancy map, which is a grid. Every element of this map says that the robot can be there or not can be there. Human engineers will laboriously do that. And when I was a graduate student, I did that too. Now, if we do that, then as soon as I finish do that as a graduate student, I will cordon off that area. Right? I have to make sure that the model that I have built is consistent in the world. As soon as I finish building the model, and that is static, therefore I have to keep the world to be that way. I cannot change the model, therefore I keep the world constant by cordoning it off, right? So fast forward 35 years at the turn of the century, that we have much more powerful sensors and technology, the laser scanners. Therefore, we can deploy robots carrying the sensors to scan the world, right? And that leads to the rise of the entire field of research called SLAM, simultaneously localization and mapping, right? And that enables us to build these models, initially 2D representations that represents at some level of accuracy of the world, and then we can use this as a model of the world to plan, right? And with the evolution of technology, then we went from even like more primitive laser scanners to the more powerful laser scanners, and we have 3D world models, and that's the high resolution and dense point clouds that, for example, companies like Google would use for navigation. Most of the autonomous driving companies will rely on models of this kind. However, let's keep that in mind, all right? So we'll build the models for the world, and we'll assume that during the entire operation of the robot system, that model is valid in the sense that it's a good enough approximation to the real world, right? And now what we want is a problem like this, that the first time you show up in the building and there isn't a model, what shall we do about that? And the gap between them, of course, is that for the generally on the left, our problem solving strategy is that to first construct the model, and given the model, we'll do planning or inference, right? And the difference between them is the information gap. On the left, we assume that we already have a model. On the right, that we don't yet, right? Now, how do we fill this gap? Well, we need to rely on diverse, rich sources of information, and not just high-resolution point clouds. And this, the requirement for the high-resolution 3D point clouds is really a major barrier for the practical deployment of planning methods in practice, at least on robotic systems. Right? And that's the reason that, for example, Google can do it, but most of the time I cannot do it because the effort of building this model is just enormous. Right? Now, however, how do humans do this then? If the first time that you come to our building, if you really don't know how to navigate this building, what you probably would find out is that at the lobby entrance, there is a visitor's map in the sense of a 2D schematic drawing of the space. And with that information, most of adult human beings would be reliably come to my office. Right? Now, can we enable robot to have that ability as well? So we're going to replace the 3D high-resolution 3D point cloud with a 2D schematic drawing of the representation of the space and enable the robot to navigate to my office. Right? So now the main technical challenge over here is generalization and variability of the environment. Right? Our office building is built on a hill, so there is wider variety of situations that the robot navigation system need to deal with. The challenges come in the form both the geometric as well as visual appearance. Geometrically, since it's built on a hill, every floor's footprint is not exactly the same. So don't think that I can go to the floor and draw, sketch something and repeat it n times and every floor is the same. No, every floor is not the same. More than that, because the floors are used for different purposes. One floor is student labs, the other floors are lecture halls, the other floors are offices. Therefore, their visual appearance will be very different as well. And also part of the building extended into the hill, so there are semi-structured environment, and then there are the outdoor environments out there. So they're all connected from the indoor semi-structured indoor-outdoor, and then the outdoor environment. So there's a wider variety of differences, variability in terms of geometry and in terms of visual appearance. And that is the challenge we want to overcome. So the idea that we have come up with is to combine planning and the learning together. All right. So the idea, in fact, is quite intuitive. So we are going to literally take in an image of the visitor's map, right? So just do a little bit of image processing and turn that into an occupancy grid, right? And then on this occupancy grid, we'll do planning can do, and use any of your favorite planning algorithm, breadth first, depth first, or A-star search. We'll search for a path in this on this grid. Right? Now, one way to think about this model is that even it's a symbolic representation, discretize a symbolic representation of the world, even though that oftentimes we don't usually think that way. Every grid point, in fact, is a symbol. It's a discrete symbol, right? And the grammar of this set of symbol is neighborhood connections, right? So that you can go from this grid point to a neighboring grid point, and that is organized in a 2D fashion. It's a special spatial grammar, right? So this is our language, and the search algorithm is the inference we do in order to infer what are the sequences that are valid in this language. Right? So this is at the planning level. At the lower level, that we have to connect this symbolic representation of a space to ground it to the physical world, right? So all the complexity of visual appearances, geometry, and all that things. For that, we're gonna do is to train a neural network navigation controller that takes two inputs. And the first input is a single camera looking forward, so a monocular camera looking forward. And the second element is this thing we call intention. Intention is a patch of the image of the visitor's map at the robot's current location. It encodes 3 channels of information, right? So a local patch of the visitor map as an image patch, and the piece of the path that the robot has just been traversed, and the piece of the path robot is going to traverse next. So there are 3 channels in information. They are compressed together into a single image, encoded into an image, right? So we're going to take this 2 input and send it into a neural network controller. Back then, we use that was like quite a number of years ago, and that is a more primitive neural network. And today, of course, that you can use much more sophisticated neural network. That doesn't matter too much. It's a neural network controller, and the input are the monocular camera input, as well as this thing we call image, which we call intent, and then an output is a command for the robot. It's a velocity direction to steer the robot to navigate. Right. So the robot will execute the command, and we are going to relocalize to figure out where the robot is after execute this command on the map, and then we can do the replanning, right? Receding horizon replanning, and we're gonna close the map, and that's roughly how this system works, right? So now the robot is going to think about the spatial representation in the occupancy grid map, and figuring out the plan and execute the action and ground it using a neural network navigation controller, right? So this design combines the learning. The learning part handles the rich visual perception of the world, right? So the camera images, all the things that the textures, the colors, and all captured, the complexity is captured over there. Now, the planning component actually is capturing the geometric complexity. We have an abstract representation of the world in terms of these grid points, 0, 1, right, and the occupancy map. And then we reason about the space and handle all the geometric complexity, in fact, the combinatorial complexity of the geometry at a high level using planning. Planning is compositional, right? So it do a search and figuring out what the path are valid. Right? This is actually a very intuitive design. And most of us, like, let's say that we are driving, follow the GPS instruction, GPS guidance, right? I mean, using our mobile phones. In fact, it is an equivalent, very similar to this design, right? If you think about this, the GPS will do the route planning, right? Your phone do the route planning. Then it give you instruction. Me as a driver, that says that okay, 200 meters ahead, turn left. But really, how do we ever know as a driver that I reached exactly 200 meters? It's just a guidance. It's an intent, right? So if you're close to 200 meters in estimation, and you look out, if there is a turn, suitable place for you to turn, then that is about the meaning, the grounding of that instruction. So all we have done is that we turned this more primitive form of the instruction 200 meters ahead to turn left into the more sophisticated intent, which is the image that captures all the local information that about the obstructions nearby and the path that I'm going to execute and I have already executed, right? So that is the intuition underneath. Now, with that, okay, so we can take a look about our performance in training.
A set of environments, the robot can navigate in new environments
on the
very
first floor
different
of
visual
the
appearance
building,
and geometry.
and we're going to test it on the upper levels. You can see the difference in terms of visual appearance, right? So one floor is carpeted, while the test environment is laminated floor with furniture that's not present over there, right? So there's one. Now let's look at its general capability. Now we put it into the real world for a test. Okay, so I think because of the network, that will play. It's unfortunate that the network connection delay. As you can go through the obstacle courses, for example, right? And also, you will see the unexpected obstacles coming. It definitely cannot be modeled correctly. As the chair suddenly appears. The robot cannot open the door, but it does know that to stop in front of the door because of the visual perception. And it knows the door is open, then go out. This robot climbs stairs, but that's not because of us. That's because of this particular robot is very capable. Now, we build all the sensor package and also the inference and the modeling on top. So everything above the back of the robot. You can interact with people as well. These are all things that are difficult to directly model. So we have to combine the model-based planning and data-driven learning to achieve this environment. This is just to show the variety of different kind of environments that the robot can handle. Now, we started thinking about maps with our visitors map, but there are other sources of information going beyond the visitors maps floor plans. So for example, how about the satellite maps? How about even hand sketches of the space? We often do that. Sometimes when we talk to other people, go this, and there's a store over there, right? Can we do that? Yes, we can, all right? But we have to rethink what information that the model is trying to encode. Instead of thinking that the model is encoding and is a reconstruction of the geometry of the world, we want to think about it. Actually tell us what to do, right? So we are going to figure it. This is actually it's a graph. The node of this graph tells us what are the salient places in the space, and the edges between the graph tells us how we can go from one place to the other, right? So this is the model that looks very similar to the occupancy graph, but even more abstract, right? So in order to construct this graph, then we have to gather domain-specific data and to train to recognize the salient places on those hand sketches and build map that way. And if we do that, we can have a robot system that actually follow a hand sketch map and navigate in a similar kind of environment, right? So it also even can be robust, be trained to be robust to people and other distractions in the environment, right? And you can see that it is localizing itself on this abstract graph and try to use that as the model for information to guide the navigation. All right. All right, goal reached. Now let's come back to our problem again. What if I don't have I don't even have a visitor's map? I don't even have a hand-drawn map. All I'm doing is I'm standing in front of the building. Does that mean then I have no prior information for about this building? Well, not really, right? So as soon as the fact that I know that I'm coming to visit me, you probably know that you are coming to an office building. So what do we know about the office building? Well, office building is a building that consists of floors, that consists of corridors and offices, right? And this is what our prior knowledge about office buildings. Today, in place of the human, we have foundation models. Foundation models knows all these kind of things, right? So we can capture this kind of information in a more structured manner in a scene graph. Scene graph basically is a graph, right? Because the nodes consist of entities such as buildings and corridors and offices and so on and so forth, right? And there's a rich existing literature on how scene graph can be constructed. However, every time you have to build a scene graph, well, but there are office buildings. Then we have homes, we have airports, and we have shops, supermarkets. Every time you have to build manually a scene graph specific to that environment class. And that's very tedious. And we don't want to do that manually, right? So we have to have a more abstract form, which we call the open scene graph, the scene graph schema. A schema is, again, a graph in a more abstract form. It consists of entities, objects, places, connectors that connects the places together, and the regions that holds the larger places in smaller places. For example, a building consists of office and so on and so forth, right? And the relations, the proximities, right? Which place is close to which, the connectivities, whether I can go from one place to the other, inclusions, hierarchies, all those standard constructs, spatial relationships that we use for inference, right? Once we have that, and we're gonna ask help from the language model to construct the scene graph automatically, conditioned on our schema, right? So this is roughly the idea, okay? So we're standing from the home. All we have know that this is a home, right? So then we're gonna ask the language model, so, well, construct my schema. What does a home consist of? Well, it tells, well, a multi-story home, it consists of floors and corridors, and living rooms, and those things, and their spatial relationships, okay? But this schema is generic to all homes, right? And now we have to further refine it for a particular scene graph instance to our specific home. For that, we'll have our robot over there to observe the world, right? And we are going to add, we'll instantiate the schema to a specific scene graph based on visual observations. And that is the scene graph, which is automatically constructed by the robot, conditioned on this schema, right? So the schema provides the abstract structural information, and combined with the visual observation of the robot system, then we get the model, which is this scene graph, and constructed automatically, right? And skipping some technical details, so the main point over here that we can construct the entire robot system, build all of from robot foundation models. That includes how we construct the models and how we do inference. The condition of the model, we can ask a language model that what is the next place to go, and further that we're going to train neural network controllers. In this particular case, it's called the general navigation model. And we connect all of them to build the entire robot systems. And some of the foundation models we use is listed over there, that in the visual, that is VQA, object detection, and the language model for reasoning. Okay. So with all this, so what we want to achieve is to generalize. We want to generalize over different kind of environments. And so there are 4 different kind of environments over here. So you can see that on the, so there is, a lab, a different lab, and then it's a simulation environment on your upper left, right? Different environments, different task objectives, find different type of objects. But more than that, I want to generalize different robot embodiment. You can see that on the left is a wheeled mobile manipulator, while on the right is a legged system for navigation, right? We want to generalize over different environments, robots, and task objectives. And this is what you have. You can see that, and we are using a single robot system to handle all these different variabilities. Sound. No, there's no sound over here. Yeah, you can see a single robot system can handle all these different situations. Okay. Right? So the point let me try to point out over here is that with the help of robot foundation models and large language models in particular, we are able to take advantage of diverse sources of information, right? From floor plans, from satellite maps, and hand draw maps, as well as scene graphs. And all of them, these sources of information that all enable us to build structured robot models with the help of foundation models, right? And it's not limited to robot navigation either. And so the same goals can be done for robot manipulation, even though it's even more challenging. And the example I want to give here is to have robot operating home appliances. Right? So we have a wide variety of home appliances, and we want to have robot assistant to help us operate all of them. Now, some of those appliances can be quite complex. Look at the control panel over there, and with partially observable underlying mechanisms of how it works, right? So even for humans, in order to use this machine, sometimes we have to write manuals. So let's just think for a second, what is a manual, right? So the manual, in fact, what does it tell us? Well, manual tells us, for example, like turn the timer, and then you want to be able to set the time. So it tells us about the variables, the state variables that represent the underlying state of the system and the actions we have performed, right? And the effect of certain actions. This is basically the structured model information we need in order to reason about how to use an appliance, right? Now, today, it used to be that robot system cannot understand the manual, so we have to explicitly code this model information. And today, again, we can automate this with the help of language models, of VLMs. We can just have these foundation models and to construct this structured model explicitly, automatically from the manual. So what we want is this structured appliance model that consists of state variables, actions, and the action effects, right? And what we do is that we're going to have the GPT to read the manual and extract this information automatically, and then we're going to ground the actions for execution on the robot. So roughly speaking, that's how the system works. The user gives some instructions, and we get a visual observation of the appliance, and then we are given the manual, and we're going to ask the language model to construct this structured state space model from the manual, and we're going to ground the actions again using foundation models to the visual observations for execution. Right? So if we do that, let me show you the results. Right? So I think I'm running out of time. We're going to test it on a wide variety of different appliances, and we're going to compare with an alternative. What's the alternative? And that's something we would all do with GPT, right? So we're going to pull the PDF file and send it into GPT, condition on that, and pushing the image as well, right? Oh, you can use Gemini, that'll be more capable, that's fine. And then we directly ask the model, what should I do next, right? Versus our alternative, which is extract the structured model from the GPT, from the manual, and then query the language model, the two alternatives. Now, you can see the difference is that the structured model and to inference leads to much better performance. Right? So I just want to point out here, even though I have the structured model, I did not do structured inference. I did not, for example, do a search or something like that. We just put the structured model directly into the large models and ask, what shall we do? And that would be a little bit more surprising to say, why would this be better? Well, it is better because structured information representation helps prediction performance, right? That makes sense, right? You can think of that as attention as well if you want. Okay, so here are some results for the robot results in action. You can see that it's trying to operate a blender, turn on a cooker, and turn on the water boiler either too, right? Let me try to summarize now by saying that, look, to summarize our results and think about where we stand and its connections with alternatives, right? So on this two-dimensional space, on one dimension is the task domain variability. I mean, roughly it says how many different kind of incidences that we need to deal with within a task domain. On the vertical axis is how much prior knowledge we have about the solution. Okay. Now, on the upper lower corner, the variability is low, but our knowledge about the solution is very high. We know a lot about the form of the solution, maybe even all the way to the parametric form of the solution. That is basically the domain of classic engineering. So the examples of those things will be like hand-designed policies, like PID controllers, or you can have a table, right, filled with all the entries. That's what we do. Now, what we want, of course, is the upper right corner, where we can handle a wide variety of different situations, the broad tasks, and we know very little about the form of the solution. And that is the open world where we want to end up with. Now, one approach to go from the lower left to upper right is to say that, okay, let's try to increase the amount of knowledge we have, and hopefully that will get to the open world. Well, that is where imitation learning and the reinforcement learning try to do, right? Gather data. And but usually they succeed on relatively narrow domains because only there we can get enough data. Now, how about open world with lots of variability? Well, maybe we can get even more data, and that is the approach of data scaling, right? Alternatively, if you look at the other direction, well, in order to handle broader tasks, the strategy of planning is to do composition, right? So the idea of planning is to have a model that encodes local pieces of information. The inference algorithm, the search, actually stitch together this local information in order to construct a complex plan, right? The search algorithm is compositional in nature, therefore it leads to compositional generalization. Now, the bane over here of this approach is, of course, that how do you get this model? Without this model, it's a non-starter. And today, the answer to this, and proposed answer to this, is that the foundation models will enable us to use lots of existing information, which are that already available there that was not usable before. That includes the floor plans and the hand sketches and satellite maps and the symbolic information that just encoded directly into the foundation models already today, right? To enable us to build the structured models that eventually that leads to the capable robots are operating in diverse, complex open world. I think that I probably end over here. I don't have time to talk about the failure resilience, but I'll just ever say that all models are wrong. Some are more useful than others, and therefore handling failure is extremely important. And it will be difficult to handle failures by models, by model them in advance, because the failures, as failures, they are out of the distribution. So unlikely they share common structural properties that we can capture in the model. So we have to deal with them in alternate manner. And let me thank the wonderful students I'm fortunate to work with, and also thank our robots. If you have an opportunity to visit our lab, we are welcome to meet all our robots and play with them. Thank you. So we still have time for questions. So I'm already sorry for running over.
Hello, can you hear me online?
So there is a question in the audience first, maybe then we can go online.
Okay.
Thank you so much for the great presentation. My question is, what we should do in the next step? Because nowadays, so many modules can be replaced with LLMs. For example, planning can be done by LLM. Image recognition can be done by LLM. And my stress is that, yes, we can improve the performance with these models. But I was often said that because this is LLM is great. it's not for your contribution. So for that in academic area, what should we do in the next? This is my question.
All right. I think I've been thinking about this all the time. I don't have an answer, but I can share my thoughts on this. Right? I think that let me take a step back. When I was a graduate student of robotics, it was just taught. I mean, I thought that would last forever, which is that a robot system consists of three components: perception and state estimation, reasoning, and control. I think that is the gospel. No one's going to challenge that, and it's going to last forever. Today, I think we stand the great opportunity to challenge that established tenet, right? I think that at this moment, it's also very uncertain, according to Dickens, right? This is the best of time and the worst of time. It is great because we can change lots of things. It is also, I think for many of us who have like so-called more experience, feel very uncomfortable. I think maybe one way to phrase your question is, what shall we do right this moment? Shall we believe that LLM will, let's say, replace search as the dominant planning method, for example? Like, let me just take this as a concrete example, right? So I think in order to try to even attempt to answer this question, we will have to characterize what is LLM as a planner, right? So what's the difference between a search algorithm as a planner and what is LLM as a planner? And this is my thought, is that I think there is major difference between them, both in terms of the way we understand them as well as the performance characteristic, okay? So I would rather say that LLM as a planner, I would not call it a planner. I would call it a plan predictor, okay? So a planner is a compositional planning, and in the sense, let's say that be very concrete, a search. It's a compositional process. It's a tree search. Every step, in principle, we can define them so precisely and to ensure that it is 100% correct. Therefore, because of that, the entire sequence, when completed, we can provide a performance guarantee of correctness, for example. Sometimes we can even guarantee completeness as well, right? All these can be done because of the model that we construct in advance. The model is the strength of the classic method, but also the weakness of the classic method. That was I was trying to present over here. I think the strength of the LLM as a planner is somewhat complementary and overlaps a little bit somewhere, of course. It have access to vast knowledge, right? I mean, if you are willing to accept some level of failure, then it can always generate an answer for you, right? Whatever you send in, tell me what's next action for this. It will tell you something. Maybe sometimes it hallucinates is wrong, and that's not good. That's why we must ground the knowledge of or common sense of the prediction into the local context, and that's why we want to construct this structured model of the local environment in order to get reliable plans, as reliable as possible, because we are doing those plan predictions. However, we will never, I don't think, at the moment, we don't have a way of providing any performance guarantee. So it does, I guess one way to try to answer your question is that I think they are complementary. We want to use both, and exactly which we use depends on the performance characteristic we want from the domain, whether we wanted the performance guarantee for safety critical applications, for example, aircraft collision avoidance systems. We definitely want that. But for others, like, what should I eat for dinner? It doesn't matter. It just generate something that if I don't like it, I say no, and the next generate the next place.
Thank you so much. It's very impressive. Yeah.
Thank you very much for your Thank you very much for your presentation and the question about this diagram. How could you spread it? Because the top of each is a minimal prior knowledge, but when we working with foundation models, it's the same as we use some prior knowledge from pre-trained data that used for this foundation model.
Yeah. So,
and of course, there are no any miracles. We should know some prior information if we want to work with one horizon tasks and use some common sense.
Right. Yeah. Sorry, I probably went through it a bit too fast, right? What I'm trying to draw here is a problem space, the characteristic of our problem. On the upper right corner, it says that there's a lot of domain variability, but we know very little about the solution structure about it. So that's exactly what you said, which is that we know very little, right? If we know very little, our information is too little to solve the problem. And to solve this problem, we must have the information. That's exactly the blue arrow on the right try to say that if we deploy leverage foundation model, using a foundation model to provide the common sense knowledge that will fill the information gap to bring us to the to a regime where we are able to solve open world problems where we need information but we don't.
Some important question for our community: should these foundation models are language model, or maybe maybe not using language and some kind of physical foundation model or some vision without language action model?
Sorry, I didn't get your question.
If we should use some language representations as a part of foundation model, or is maybe some kind of physical models without any language representation?
Okay, I mean, the short answer is, of course, we would very likely use all of them. The real question is how the selection is to be made. What are different characteristics, especially in robot systems, and what are the choice biases could be, and how we should make those choices, right? So here is my thinking, right? I still think, at least in terms of the old-fashioned ways, at least conceptually, whether you implement it that way, that's a separate issue. Conceptually, we should think about, in terms of robot system, is to absorb the information of the physical world, encode it in some internal representation, reason about it, come up with, at some abstract level, the action we need to take, and then ground the action into the physical world for the execution. Okay, so this is still how I think about my problem. But of course, there's debate about this. One of the premise, let's say, of the VLAs, for example, visual language action models, is roughly saying that we do not need to explicitly encode the internal representation. I don't want to impose any priors on the structure of the internal representation. That's a debatable issue. We'll leave the debate out there. I'll just present my view. Okay, I believe that the imposing a structure on the internal representation is exactly the leverage we have, and that going to lead to performance improvement that's very substantial. Now, why do I say so? For example, the human language or language models is not just some kind of it encodes a particular kind of prior. The kind of prior is what kind of concepts, what kind of things are useful in practice. Right? A lot of time we think of language words as just basically a means for communication, but communicate what? Communicate those things are useful. Now, taking advantage of language model to do reasoning and so on and so forth is one thing, but taking advantage of those language concepts and use that as a source of information to build our models. In fact, we are simultaneously build more useful models, and we should take advantage of that. This is my thought. I think there is one question. Okay. Just 2 minutes. There's a question online. I think we should answer in the end.
Yeah. So the work here is already quite close to our dream that having robots working at home. Then what do you say are the missing pieces that really enable this? Like, is this just hardware not good enough, or the LLM or some other pieces we are missing?
I think that we are quite distant some distance away from a robot at home. All right, so at least we should put things in calibration. I would say that autonomous driving robot taxis probably are not far away, and we are at least one order of magnitude further away in terms of a home service robot at home, right? And I think that I mean, in order to do useful things at home, for example, iron the clothes and cook a dinner and play with children and alert the hospital if the elderly person falls. This variety of things, if you just think about it, this is substantially more, order of magnitude more than an autonomous vehicle that drives on the road. The road is still relatively structured, even though that's already hard. But the kind of variability on the road is car drive around, right? So I think one of my friend at Google once told me, well, driving is very, very hard. But one thing simple about driving is there are only three things you do: turn left, turn right, go straight, and stop. Okay, 4 things. But think about all the difference that can change that at home, even though you have all the common sense knowledge over there to manage this complexity and be able to manipulate. And the set of things we do at home is just vastly more than on the road, and the exceptions. But I didn't get to talk about that. The failures are just a lot more than on the road. On the road, with that set of failures, the so-called the long tail, we are already encountering difficulty to deploy robot taxis in many places. But at home, that will be further. And then, by the way, I want to compare with why is that robot systems one of the earliest success of large-scale industrial deployment robot systems. Where? It's in factories, right? It's in factories that we can control everything, get rid of all the variability, and make sure that things move exactly the way. Only those things we want are there, and they move exactly the way we want it. That's why robot system deployed very successfully in large scale back in the old days. Today we have went beyond that, but towards the long-term vision of having robots at home that as domestic helpers, for example, I think we still have many technical challenges to overcome. In particular, I mean, in short, variability, I would say, generalization and variability. Foundation models helps, but that up to a certain level of scale and the details. Online, there's an online question. Hello, are you still there?
Yes. Hi, this is Harsha. A wonderful talk, Dr. So thank you for the talk. I was wondering, traditionally when we were looking at training deep learning policies, we saw that for spatial navigation or for any kind of even in 2D grids, we saw a difference in performance based on the egocentric versus heliocentric view of the world. I'm wondering if there is any such difference now with the foundational models, is there any particular representation that is better now that we are using, very high dimensional representations?
Yeah, I think that's a very interesting question that has to do with how we decompose the robot system or control policy into components. All right. So again, the constructing 3D world models as a precondition for reliable generalizable robot performance, that was at one time held as a tenet of robot systems. And that was why we learned when I was a student, I was learning about computer vision, and the entire community of researchers devoted entire careers to do things like that. But one way to think about this today is that what does those VLA models actually do? What they do is to do shortcuts. You can think underlying, at least conceptually, the system consists of state as perception, state estimation, reasoning, blah, 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 those components all together, right? Now, imagine these are all functions. Once they have been constructed, you can compile away the details of function and have an alternative approximator that is much simpler, but was a good approximation of the original compositional construction. That's entirely possible, at least from a mathematical angle, right? Now, it is in the original compositional construction that the 3D reconstruction plays a critical role. Now, if you take the compiled version and want to do approximation, likely you don't need to go through the 3D reconstruction. If we do that, then of course that we will lose some generalization, right? Because look, think about the benefits of 3D reconstruction. As soon as you have that, you can look at the world from different view angles. You can plan from any place to any other place. You will figure out, regardless of where you are in this world, where to go next. But if you do compile and you want to have a simple approximator, then what do we hope for? Well, we hope for things like from an egocentric view. For example, I want to grasp the object, right? Think about, so I'm in front of this obstruction. If I want to have an object behind from an egocentric view, what I can do is I know that I can put the arm right behind, goes like this. But this motion, you can illustrate this as a curve on a 2D projection of the egocentric view. This is much simpler. It does not require 3D reconstruction. However, at the same time, as soon as the obstruction in front of me gets more complex, then I would not be able to do 3D reasoning. So that is a trade-off, I think. And this is an interesting direction to explore, not clear to what extent it will succeed and what is the trade-off. We'll lose some generalization, but with limited amount of data, I will get a reasonable performance within a more limited domain.
Thank you.
All right, so let's thank you.
Thank you.
Thank you so much.